Hi there, my name is Jay Riley, and I'm going to be presenting the UAlberta at SemEval 2024 Task 1 paper. So our paper is called A Potpourri of Methods for Quantifying Multilingual Semantical Textual Relatedness and Similarity. There was a big group of us, but we were sponsored by the NZERC and by Amy Institution as well. All right, so before we get into it, we have to define some terms. So we're going to start off by defining semantic textual relatedness, STR, which is a broad term for measuring the degree of commonality between a pair of sentences. And we're also going to define semantic textual similarity, which we define as STS, which measures the degree in which pairs of sentences are close in meaning. So here we can see semantic textual relatedness measures the overlapping topics and words of two different kinds of sentences. And when we're doing semantic textual similarity, we have the overlap in overall meaning of the two sentences. So here we have a couple of examples. So our first example, when I tried again, I was able to juggle. And our second sentence, when I went back to it, I was able to juggle. Both of these sentences share really high relatedness between the two of them and really high similarity. So they have very similar meaning and very similar content between the two sentences. The only difference is this first part, when I tried again and when I went back to it. Then we have the second set of sentences, old car driving down the road and two old women enjoying it at a gathering. These two sentences have really low relatedness between the two of them, and they also have pretty low similarity. So the overall meaning in the two sentences is very different, and the topics and the words between the two sentences are also different. These examples were taken from the SemEval 2024 Task 1 English Training Dataset. So in our paper, we have two different hypotheses. The first one is similarity is a special case of relatedness. So as we can see, we believe that relatedness is this more broad categorization that two sentences can share, where we have similarity being this more shallow special case of relatedness. So here we have an example that we took from the SemEval 2017 Task 1 Track 4. So this is an STS data set. And the first sentence is, and in the United States, we're considered Mexican. And in the second sentence, we have in the United States, we are considering Mexicans. So if we look at the two sentences, we have high relatedness between the two, but the overall meaning of the sentence is very low. So they have low similarity. So the first part of the sentence is identical between the two, and we also have the overlapping nationality between the two sentences. But this part here, we are considering and we are considering are two very different things. And so the whole meaning of the sentence changes. So our second hypothesis is that relatedness and similarity are preserved under translation. So first here we have these two pairs of sentences. It is better known as a walk, and it is also known as a walk. So we have a lot of similar words between these two sentences. It is known as a walk, and the only difference is this better and also. And so this hypothesis claims that when we translate one of the two sentences into another language, we share this relatedness and similarity. So here we have the same two sentences, but now one is translated in Spanish. And in our third example here, we have one that's translated in Afrikaans. And if we look at it, we can see that the sentences share the same amount of relatedness here. On our right here, we have this score of 0.88, and this is the relatedness that's given between these two sentences. And as we translate the sentence to Spanish, or if we translate it to Afrikaans, we can see that the sentences still share this same relatedness. All right, so for our method, we actually have 10 different kinds of methods that we went through, which can be categorized into 4 different types. So we have explicit semantic, which create and compare different semantic relationships of each inputted sentence. We also have an extrinsic method, which uses the output of systems designed for other semantic tasks. Then we have distributional methods, which can create and compare embeddings of different pre-trained language models. And then we have large language models that we either access through prompting them, or we combine the multiple model outputs. So in each models, we have, for the first one, explicit semantic, we have word overlap, where we measure the different words between the two sentences. concept overlap, which we actually will measure the different content words in the sentences and see which of those overlap. And then we have abstract meaning representation. For extrinsic, we go into paraphrase identification, and we also look at natural language inference. And then when we're in distributional, we use two different kinds of embeddings, which we will go over in the next part. And then for the large language models, we will prompt the large language models. We will fuse different kind of language models together, and then we will fine tune different language models. So here we have the different resources that we use for these language models. So when we're using, different methods, when we are doing word overlap, we use a bunch of different Python libraries. Concept overlap, we actually use a WSD system. For in this instance, we use Amuse. For AMR, we use the Sapienza API. When we are looking at extrinsic methods for paraphrase identification, we look at Roberta, and from that, we use a fine-tuned PI classifier. When we are looking at NLI, we are using a Roberta with an NLI classifier. For our different kind of embeddings and our distributional methods, we are using BERT for our embed B, and for our embed R, we are using Roberta. And then when we go into our large language models, we use ChatGPT for our prompting method. For our fusion, we use a bunch of different open source LLMs. And then our fine-tuned models, we use T5, GPT-2, Roberta, and MPNet. So our best results that we report is from a regression ensemble system where we use the 4 fine-tuned models that we just went over before. And in this ensemble, we treat each score as a feature in a linear regressor. So here you can see we have our T5, our GPT-2, Roberta, and MPNet that we just went over, and we patch each of the scores from these methods into a linear regressor. All right, so we're getting into the results from our method. So for our STR results, here we have a graph. On the bottom, we have the English the STR data sets, and then we have the average of all of the languages that we accessed for track A. And then on our y-axis here, we have the Spearman correlation. So if we look here at all of our different bars, well, first we'll see here in the brown, we have the LABSE supervised method. So this is the baseline method for the overall task that was created by the task chairs. And then our method here, our best method is the target XGM and the XGB for MS. And we actually were able to achieve SOTA results for the English in all of the data sets. Now we'll take a look at STS, so our semantic textual similarity. And so we're going to be looking at the STS data set from the SemEval 2017 task 1. And we're going to specifically be looking at track 5 and track 4A. So we can see on the bottom here, we have English to English, and then we also have an English to a Spanish data set. So track 4A had one sentence in English, and the second sentence was actually in Spanish. And we are going to be comparing this to the ECNU data set, which actually is reported in the Pearson correlation. So we are going to be reporting Pearson correlation instead of Spearman as we did previously. But the important thing to note here is that all of our high achieving methods that we previously saw, so our prompting method, our fusion method, and our XGB for MS, which is our 4 fine-tuned ensemble method, outperforms the previously reported results for this data set, both data sets. All right, so now we're going to take a look at STR versus STS. So this is actually going to go back to our first hypothesis, which was that similarity is a special case of relatedness. So as we look at these ones here, we can see at the bottom, we have all of our different kind of methods. And then on our y-axis, we have our Spearman correlation. So first, we're going to be looking at the STR English to English. Then we are looking at STR English to Spanish. And then we are looking at STS English to English and STS English to Spanish. So we're going to be doing a little cross-lingual comparison here, but we are also going to be looking at data sets both in relatedness and similarity. And as we can see at these lines here, we have a really high correlation between the performance of our methods for the relatedness versus our similarity. And we believe that this correlation is evidence for our hypothesis that similarity is really a special case of relatedness. So now we're going to be taking a look at our monolingual versus our cross-lingual. So this is our second hypothesis. So as we can see here, very closely related. We have our methods on the bottom, and once again, our Spearman correlation on the y-axis. We're going to be taking a look. So this is STS, once again, is that 2017 STS data set from SemEval task 1, 2017. And then we actually have our English STR data set, the Spanish STR data sets, and then we have our STR English to Spanish. So for this STR English to Spanish data set, we actually translated one of the sentences from the English dev set into Spanish. So we'll have one sentence in English and our second sentence in Spanish. And then we evaluated our methods on this. And we can see that for almost all of our methods, we have this extremely high correlation between the performance of all of them, with some such as PI outside of its performance on Spanish is very close on all of our data sets. And we believe that this will prove that our hypothesis is correct, that both similarity and relatedness are preserved under translation. All right, and our conclusions. So overall, we have ensembled a variety of methods on 2 sentence-level semantic tasks, both in the monolingual and the cross-lingual conditions. We also achieved SOTA results for all of the English tracks, and we also performed top 3 on 16 of the language track settings, which is pretty impressive. We also provide evidence for 2 of our hypotheses. Semantic similarity is a special case of semantic relatedness, as well as similarity and relatedness are preserved under translation. Thank you very much for listening to the presentation. And at the bottom here, we have a QR code in which you can access our GitHub repository. Thank you.